Hi, everyone. So the talk is called Integrating Existing C++ Libraries into PySpark. So a little bit about me. My name is Esther Kundin. I'm a senior software developer at Bloomberg. I'm the lead architecture and engineer on machine learning and text analysis teams. I'm going to be talking a little bit about the project that I've been working on, and I'm also an open source contributor to Hadoop. So a brief outline of what we're going to cover. First, we're going to talk about why bother? Why would you ever want to integrate C++ into PySpark? So we're going to talk about a real-life use case that I encountered. Then we're going to have an overview of PySpark and how it works. And then we're going to talk about specifics on how to interface with your C++ code with some code examples. We're going to pull it all together for you with all the things you need to know to make this work. Then we're going to talk about some of the challenges and a few C++ tips and tricks to make this integration process less painful and more seamless. We're going to cover some takeaways and then a Q&A at the end. So that's a lot of bullet points, so I'll make sure to talk really, really fast to make sure we cover everything. All right, so the real live use case. So the system that I was working on is a news sentiment system. So it's a real-time system that processes news stories as they come into the Bloomberg terminal. Bloomberg is both a content provider for news as well as a news platform. So there are a lot of news stories coming in. And our product computes a sentiment score using an ML model on the stories to try to figure out whether the companies mentioned in the story, was the story supposed to be a buy or a sell? All right, sorry about that. So what we're looking for is something that's under 10 milliseconds to make the prediction, and then we stream it out very quickly to our clients. So the actual implementation of our model is written in C++ so that it can be computed very, very quickly in real time. And what we had wanted to do was to also be able to take this exact model without any modifications and then run it over our historical data. So the historical data is about 2 terabytes of compressed text. And again, we want to run the model that we already had built, which was in C++, over this data. And the SLA that I was given was we want to be able to compute everything on this model in under 24 hours so that when we come up with a new model or we're backtesting something, we can very quickly iterate over all the data that we have. And then as we develop new models, we can then also retrain, we can retest. And if we wanted to do this something like weekly or monthly, we'd be able to do it very fast. The system beforehand didn't even exist. And then we had calculated that if we would just try to run it serially over all our data set, it would take about a week. So we wanted to make sure that we can do this faster and in a scalable manner so that as our history grows and more data and data sources come in, we can still do this effectively. So now a quick PySpark overview. How many people here use PySpark? Okay, so we're going to do this really fast. So as you guys know, PySpark is just a front-end wrapper to the Spark system. Spark is running in the JVM. And if you use PySpark with the data frames API, basically what it'll end up doing, if you see in that picture, is it's going to wrap your Python calls and then run them in Py4j over the Spark context on the driver, send it out to the executors on your cluster, run your code. So if you stick to existing APIs, you do add a little bit of overhead, but not too much. However, the power of PySpark also comes from running user-defined functions. There were actually a lot of talks in this room about this earlier today. So for the user-defined functions, they allow you to run the native Python code that you have compiled on your workers. But the way that that happens is that when you define your functions, they have to be sent over from the driver to the executors, and the function itself has to be pickled and passed over. And then, because the executors are also running in a JVM, and they need to talk to Python workers to execute your code, they need to send your Lambda and then your code row by row to each of the executors. Then you serialize it back to the Spark workers, then they're going to send it back to your original program. So as you can see, it's going to be a lot of overhead in terms of serializing your data back and forth as you pass between the JVM and Python divide. So there was actually a talk earlier today In fact, I think there was probably 2 talks earlier today about new Spark support for vectorized UDFs with arrow format. So if you happen to be using things like pandas, there's other ways of making this work a lot faster so that there's no need to serialize your data between the Spark worker and the Python worker on your cluster. However, if you're not using pandas, that doesn't really help you. So how would you interface to your C++ code? So in general, when you're interfacing between C++ and Python, you have a list of options. One of those options is Swig. This Swig is really powerful and mature. It's an interface that actually supports nested types and classes, and it's language agnostic. You can actually write interfaces to your C++ code to Python as well as Java or other languages. The cons for that is that it's a little bit more complex and requires a little more work from the developers. You have a special .ini file that defines how your data is laid out, and you have to have extra steps before you link your code. Your other options are using something like Python, which basically runs with a different backend for Python, but that involves a separate install. You can use something like C-types, which is really straightforward but pretty limited in what it can do, and you can use CFFI, which is pretty easy to use and to integrate. Your other option when you're interfacing with your C++ code is actually just to use the JVM directly and not use PySpark at all, saving you that JVM to Python serialization and deserialization. And you can use your C++ code with JNI, the Java Native Interface. So then you can talk from your C++ code, you can talk directly to Java. So then you can actually write Java code that calls Spark and then uses your code. In fact, Spark ML BLAS implementation using Netlib uses this interface. So this is definitely something you can do, but if anyone has ever here written any JNI code, it's actually very clunky, difficult to maintain, and hard to use. So it's one of those things that you don't really want to do more than once. Your other option is to use Swig. As you can do with Python, you can do the same thing with Java and call your C++ code via Swig directly from the JVM rather than from Python. Or another option is just to use a pipe command where you can basically use system pipes for standard in and standard out, and then you can run any executable, C++ or otherwise, to work on your code. This is definitely something you can do, but it's a little bit brittle, and I wouldn't productionize my code that way. So in our group, we actually chose the Swig and PySpark, and we're going to run through the example. So why we chose Swig and PySpark were a few reasons, and these were actually mostly institutional reasons for us. The first reason was that for our C++ code, we already had a Swig interface written because our model builders test our code with Python wrappers already. There's a lot of institutional knowledge of C++ and Python. There are very few people where we are that know Java or Scala and are interested in learning and maintaining code in a completely separate code base to write the glue layer that will run these models. So for us, it made a lot of sense to stick to languages that people were comfortable in, especially because this is something that runs in the back end. This is not a real-time system, so even though it is less efficient to run it this way via PySpark, it'll be much more efficient to develop and maintain, and the hit that we took was not great enough to really, make a huge impact. And since our final run did run in less than 24 hours, even though we could make it faster, we decided that this is actually good enough. So with that, we're going to go through an example of how you would actually go about doing this. So this is an example of what Swig workflow looks like if you want to run your code with Swig interface. First thing you would do is you take your C++ code, and then you would have to write a separate interface code that defines the functions that you want to be able to call through Python. You take your 2 files. You'd call Swig on your file to generate code. You would then compile and link the generated code along with your C++ code, and you generate a shared object and a Python wrapper. Afterwards, you can then take any other config files that your program needs. You wrap it all together with something like zip or tar. You create your .zip or .tar and your archive object. And then during your run, this is something that you'd want distributed to your cluster. In our case, our cluster is running with yarn over HDFS, so we would want to deploy the .zip to HDFS because this artifact now needs to be accessible from the entire cluster if this is the UDF that you want it to call. So with that, we're going to take a small toy example to show how this would work. So we're going to start with this example that was on the Swig tutorial. Let's say you wanted to write your own function that will calculate a mod. Obviously, you're not going to do that, but you can imagine other functions that you would need to use. So let's say you had your C code, the one that you wanted to run was here. Then you would need to generate your interface file that would show which function, the function prototype that's going to be accessible within the Python. So here, you would use the .ini format to generate a file like this that basically says, I'm externing my mod so that it's accessible from Python. And the Python module that it's going to go in is going to be called example. So these would be the two pieces of code that you would have. And then you would call Swig and tell it that you want Python code using your example.i file. At that point, you would want to link together your actual example.c and example wrap.c, which was generated in the previous step, and then link your code. And you finally come out with an example.so. And then, if you wanted to test it, you can run your Python interpreter. You can import your brand new example module, which is a Python module which has underlying C++ code. And you can call it, and then 7mod3 is 1, so we're happy. So that seems to work. So far, we haven't hit Spark at all. This is just how to use Swig. At this point, we now have to wrap everything up and ship it to our cluster so that it's available. So we'd want to zip up our shared object and our Python wrapper. And then we want to write our PySpark program that calls this UDF. So we would write a quick function, such as calculate mod 7. We would want to, you want to run system.path.append for the example because you are going to have your code locally in your local directory, and you need to tell it where to look for this new module. It's not going to be deployed with everything else. Then you'd want to import it and then call it. So this is going to happen inside your user-defined function. And then you would write your main wrapper where you can start in the driver, you can start a Spark session, you can read some input data, you can then wrap your UDF. And then, for example, what we could do with it is take our data frame and add an extra column which calls this function on it, and then write our output to some file. So with this PySpark program, here we go, we're going to write our output to HDFS. And with this program, we would run it via Spark submit in cluster mode. And here's the important bit. You need to pass it the archives example.zip hash example. What that tells it is to take your zip file, and then when you're on the cluster, expand it into a local directory in your working directory where Spark is running. And you expand it into the local example directory. That way, you can import it from within your UDF. You'd also need to give it an extra library path example so that Spark knows where to look for the Python modules. And then you pass it your Python driver program. So that was how we do a very, very simple example with Swig. So let's say we wanted to do something more complex and we want to work with environment variables. It's conceivable that your more complex example of the program that you're going to be distributing can have configuration that's dependent on environment variables. So how would we do something like that? So here we have another example for the mod where rather than taking both the x and the y from the parameters, we're actually going to take one of them from the environment variable. So please note, do not actually write code like this. I do not recommend doing a to I on some random number that you get from the environment. This will probably crash. So don't do that. But assuming you have more robust code that does use an environment variable, this is what it would look like. So you can update your actual C++ code to get the environment variable. The interface changes a little, right? You only have one integer being passed in. Our module is now called example2. And then you do the same thing as before. You'd run swig, and you'd generate your .so, and you'd have to run swig and compile and link everything as before. And then your user-defined function is now changed, where you're just passing one value to it, same as before. And then when you would actually go to execute it, we'd still need the archives example2.zip. We have to tell it to take the zip and open it up locally. We have to set your extra library path so you can find it, and Python can find your library. And the important part here is that we can actually set the environment variable right there. So what this does is that's going to pass the environment variable to your executors, and then you'd call your Python program. So note, this only sets the environment variable in executors. The assumption in our code was that you don't need it in your actual driver. If you did, there would be a separate parameter for that. Okay, so now we've got everything working, and we're going to say, well, if you think about it, it was really inefficient where we were actually pulling in, doing the import statement inside the UDF. So that means we're doing it literally once per row, calling and loading this module over and over again. So what if we actually pulled it out to the top, did it once, and then just called it in the UDF? So we can't see my mouse pointer, but the idea is that you'd pull it out. So if we did that and run everything as before, we'd get a whole load of really, really bad error messages, and buried deep inside you get something like this return statement where something with pickling is not working. What happened? So the basic idea is that when we pulled the code out over here, that piece of code is run on the driver. The UDF itself is run on the executor. In order to get the data from the driver to the executor, it's going to pickle the object and pass it along. However, our C++ module is not pickleable, so it's going to have problems serializing that and sending it over. So because of that, we're going to have to figure out a way of getting around it. In general, if you have any interface that's pickleable, you're okay, but a lot of interfaces to C++ are going to have these problems. So you can try to write your own serializers. You can try to set Spark to use a different serializer. But that is a lot of overhead and very difficult. So your options are actually fairly limited. You can try not to keep any state in your C++ objects and just literally pull them in every time. You can try to use pandas and Apache Arrow and vectorized UDFs and see if code works, which is more efficient. But again, that's not going to really help you in C++ world. But the other option is, rather than pulling in the data once on the driver, you can try to do the import once on the executor, either with a Python singleton object. So you'd have to import some kind of Python singleton package or implement your own. And that would cause that even though your code is called once per UDF, you'd actually only instantiate that module once. Or you can use map partitions. So in that case, you would be able to just import the code once per partition and then run it row by row, which would be more efficient than importing it once per row, a little bit less efficient than singletons, but not too bad. So because singletons aren't natively supported, I decided to just work with the map partitions and see if I can get my SLA that way. So what that would look like is creating a separate class that can do something in the setup of the class that would just import it and save it once, and then make my UDF wrapped in one function. So you can see that the process partition is called once per partition. At that point, it's just a generator function that runs over the rows in that partition. So you would actually call, that once per row. So you'd have your for loop going through the rows. And then in that do process that's called once per row, you have it, again, calling the my_mod example. So if you create something like that, then in your actual driver program, you don't need to import anything and pickle it and have those issues. You would just create your data frame, and then you would call df.rdd.mapPartitions, and you'd pass it your partitioner's function. So what this will do is it will import the module once per partition, and then for every row, it'll just call your UDF. So this is much more efficient than doing it the other way. So now, putting this all together, what do we need to know? In general, you need to create shared objects for your C++ code. This is really important. You need to ensure that your compiler toolchain matches where you generate your SO and the Spark cluster, because in general, you may not be working on the cluster itself when you're writing this code, so you need to make sure that it matches. And then you need to make your .so available. So you need to have it deployed to HDFS on the cluster or have it installed. In my case, because the cluster was owned by a team that was not my team, I wasn't able to just go and install my SO somewhere locally on the machines. In that case, that's why I was passing it as an archive through the rest of the executors. You'd also need to deploy any needed config files if your code depended on it. And the last point was also important. If there's any libraries that your code depended on, C++ libraries that were not deployed on the cluster natively, you'd need to package that together. So in my case, I actually did have other native libraries that were not on the cluster, because there were a lot of other libraries included in our model. So I needed to actually package all of that together and then ship it to the cluster for the actual run. And then again, you have to remember to pass any environment variables that your drivers or executors need on the command line. So all the options that would be relevant here would be things like the Spark executor extra library path, which will tell it where to pick up the C++ libs. On the executors, you have the same thing for the driver. The -- archives let you pass your shared object out to all the entire cluster. The -- py files is another option for how to pass your data. If you wanted to split your executor and driver Python code into two separate programs, you would pass that separately. And on the bottom, you were able to set the environment variable with Spark executor env.environment variable for your executors, and you set Spark yarn appmaster env environment variable for the driver that's running on the application master. And then you would run it something like this, where you'd have to run Spark submit. You'd have to set your library path on the executor to be able to pick up the SO that you passed it along. You'd need to do that on the driver as well if you were picking up your SO on the driver. This would be the important part, where you're sending your SO config files and everything else together over and telling it the name of the directory under the current working directory that Yarn will create for you. You'd set your executor environment variable. You'd set your driver's environment variables. Then you'd actually run your Spark driver code. And then any parameters that your code needs would be over here. And that way you can run your entire package together. Okay, so now some of the challenges that we faced in this project. The first issue was that Spark sets the number of partitions heuristically, and that may not be efficient. So remember, we were running with map partitions. If Spark sets the partition number super high, then you're going to be recreating that data again and again. And if it sets it really low, then your job will take forever to run. In general, I think as most PySpark developers will find, it's very difficult to get it to use the number that it sets automatically, and a lot of heuristics are usually needed to be able to figure out the correct partition to use for your specific data set. The other issue is that you have to make sure that your Yarn Python container has enough memory to load your SO and its config files. So if you remember, if you're using Yarn, every container has memory set, and then the executor itself is using a lot of overhead. So you need to make sure that when you allocate your Yarn container's memory, you actually have enough space for your Python worker to run, because it's also running under Yarn. So in order to get around this, you need to repartition with dataframe.repartition and set your number of partitions. It's usually efficient to set it equal to the number of executors that you have. That way you'll basically get very similar results to using a Python singleton. And you'd also want to set your driver memory by calling executor memory and setting it explicitly to make sure that you have enough space for all the things that are in your zip file that you're shipping over. Lastly, we've got some C++ tips and tricks. So if we remember this picture that I showed earlier where we have a pretty convoluted deployment and integration process where we write C++ code, we have the Swig interface code, and then we kind of generate more code and then compile and link it all together and wrap it up and ship it. You could imagine that if you wanted to change your C++ API, you would need to change your API, you'd need to change your .ini file, you'd need to rerun Swig, recompile everything, put it all together, and then ship it and do it all again. So you can imagine this would take a really long time, and you don't really want to be touching the interface very often at all. So the idea is, if you write your C++ code in such a way that you have your API basically set and it doesn't have to be changed a lot, you don't have to rewrite your .i file, and you don't have to recompile it. You'd also want to see if you can not change your C++ implementation code also, because then again you would have to recompile and redeploy everything, and it's actually quite complex. So the trick that we used was we actually generated our model code in such a way that we were able to set all the other hyperparameters and a lot of the workflow of how the model is run in config files. So imagine kind of setting all your hyperparameters in the config file and then writing all the code in such a way that you kind of have a DAG of processing where you just specify in the config which blocks of code you're going to run. So if you do it like that to then rerun your model with different parameters, all you need to change is one config file. You don't need to recompile anything. You don't have to figure out what libraries the thing links into. You don't have to see if all of a sudden it links in some new library that you don't have deployed, and now you'll have to pull that in and package it. You just change one text config file, update your zip, and then ship it and run it again. So using a system like that will make this whole process a lot less painful to use. So in conclusion, we were able to run our backfill on our entire data set with our C++ model in less than 24 hours. I believe last time I ran it, it took about 20 hours. And we were able to generate backfills on new models iteratively. Soon after finishing this project, we came up with 3 new sets of models, and we were able to iterate over them very quickly, changing things as we went along. And the backfill of our data was actually the easiest part of that process, which is what we were aiming at. So some takeaways are that Spark is flexible enough to even include your old C++ code. You need to deploy both your C++ code and everything it depends on onto your cluster in some way. You got to tweak your Spark submit commands in order to be able to actually pick it up. And it's important to write flexible C++ code so you can minimize the overhead and the churn every time things change. So with that, we have, I think, 3 minutes for questions. And also, we are hiring. Please check our careers page. I will be at the booth downstairs. There's a job on the job posting. We would love to talk to you guys.
Thank you very much, Esther. Any questions?
So you said that you chose Swig because you already had it in-house, but it looks really like a lot of work to me. So looking through that original table, it looked like I'm looking at CFFI. Is that a lot easier to implement to do, or is there still all these steps?
So as far as I know, CFFI is a lot easier to use and a lot of what the community is using. I think I haven't tried using it in our context, so I don't know if there's any like secret gotchas that will make it not work. Because I haven't tried it myself. But I do have to note that although Swig looks really horrible, if your actual API layer doesn't change, you only have to write that horrible file once and you are done.
Okay, all right, thanks.
Anyone else? All right, thanks again, Esther.
Thank you.